A controlled variable, that's something that can't change. So I'm talking about rolling a ball down a ramp, and I'm changing the height, and it has an impact on the time. I'm going to leave the mass of that ball the same, right? That way I know that it's only the height that's changing the time. If I start putting more massive or less massive things to roll down the ramp, that also might have an impact on the time. So I would want it, or if I'm dropping stuff. If I drop a bowling ball from 10 meters, and then I go to 20 meters and I drop a tennis ball, I don't know what's having the impact. But if I take that same bowling ball and drop it from 10 meters, and then drop it from 20 meters, and then drop it from 30 meters, I'm pretty sure the height, if there's a change in the time, there's something there. That's the pattern I'm looking at. If I change the bowling ball, then I'm going to have to figure out if that's what's causing any change or pattern. So a controlled experiment only allows one variable at a time to be changed. So when I do research at Notre Dame in the summertime, we only change one thing at a time. We're curious about a million things, but we only change one thing at a time. That's it. Just one thing at a time. What happens if we change this one thing? What happens if we change this other thing? I was doing the summer before last, we were making polymers. And we were we were doing cross-links. And there's a chemical process, there's a synthesis that takes place where we're kind of infusing other molecules into other polymer structures. And it takes time. It takes hours to do this process, and we know that if we leave it in there longer, we'll have more of these cross-links. We know if we don't leave this process alone and we hurry up and we do it for a shorter amount of time, we'll have less of these cross-links. Did we know how many? No. But we used the same polymer, and we used the same material that we were making the cross-links out for all the different times. So we did one at 2 hours. We left that last process for the conversion at 4 hours, then at 6 hours, then at 8 hours. Then we went back to look to see how many things are cross-linked. Okay, so it was controlled. We only changed one thing at a time. In this particular case, we changed the time. The materials were the same. The process was the same. Everything, we weighed it out precisely, so everything was the same. The only thing that changed was the time, as much as humanly possible. So step 4 of the scientific method is draw a conclusion. Okay? What does all this information mean? I'm starting to hang my posters up from Notre Dame. When I hang them up, you're going to see that scientific method and process in a variety of research things where we have an idea, it's based on something else. We have a question, what happens if we change this one thing? We do a bunch of experiments. We look at the data. After the data, we say, oh, this one thing does this, or oh, this one thing doesn't do anything. If we determine that the hypothesis is correct or not, that's the main thing. Were we right or were we wrong? That poster I just hung up was about thermoconductivity of things as they go through different phase changes. So think of a wax. A wax can actually conduct heat, not as much as like metal does, but it does. But when it melts, it becomes a liquid. So it's a solid when it's wax, but when it melts, it's a liquid. Does it conduct heat as much? No, it doesn't, turns out. And we can even raise the temperature on that wax high enough to make it a gas. And guess what? When it's a gas, it's not good at conducting heat. So the thermoconductivity of that wax changes as the phase of the wax changes from solid to liquid to gas. That was the theory we had. turned out to be true based on the data. If the hypothesis, now if I were to do that research and I didn't get those results, I'd be like, uh-oh, that doesn't work. And so I'd have to come up with something else. But I still learned something, right? I learned that my hypothesis was wrong, but I still learned something. I wasn't right, but I learned something. So even in science, even when our hypothesis is wrong, we still learn stuff, right? Think about that. We still learn stuff. Step 5, develop a theory, well-tested explanation. So I was helping a professor at Notre Dame, and we were doing this thermal conductivity for phase. And as soon as I showed him the results, I said, I don't know, does this seem right? He goes, oh no, that's good. That's publishable. That's good. That's good stuff. And I said, okay, what do you want me to do next? He said, do it again. And again. And again and again. It was well tested. That's all I did. I go in, get there early in the morning, set up my equipment, run a test. Go to lunch, come back, set up another test, run another test. Right before, somewhere in the afternoon, I'd go for a walk. Usually I'd have to pick up supplies and stuff like that. And then when I'd come back, set up a third test. The whole summer, ran it over and over, and you can see the data over there on that poster. And that's basically what I do every summer. Once we figure out that it works, and so then they actually did start to develop a theory and an application for that. But that was done over like 10 years ago. But if you think about Isaac Newton, he kept dropping stuff, and he realized that force, gravitational force, accelerates everything at a constant speed. Well, I should say a constant acceleration. That was centuries ago. We still can't. It's not wrong. So sketch this out in your notes as best you can. Okay. What is the whole thing? What are we talking about? Well, the scientific method is, first you make an observation, right? You make an observation. Oh, that apple fell down. Then you ask a question. Is there some sort of pattern to the way the apples fall? Then you develop a hypothesis. You know, I think everything falls. I wonder if there's a way that they fall. I wonder if there's a pattern. Everything that goes up must come down. Test that hypothesis. Throw stuff in the air. Somebody on the internet told me gravity wasn't real. And I said, well, take a hammer, throw it in the air directly above your head. And let me know. Because he's arguing, he's like, you're not a real scientist. You're a high school teacher. I said, well, I've done some research. And he goes, you're a high school physics teacher. And I said, well, okay. I said, well, you're not, you're not a scientist either, but do me this favor, go outside, take a hammer, throw it up directly above your head and just stand there, and then let me know if gravity's real. Okay?
What did he say to that?
He stopped arguing with me after that. Right? Because we know it. Because it's been tested over and over. So, and I'm being a little facetious. Please do not go home and throw hammers above your head and then tell your parents, come on, guys. We got to use some common sense. But test the hypothesis with an experiment. That's basically what Newton did, is he dropped stuff. He threw stuff. He dropped stuff. He rolled stuff down ramps. Right? Over and over and over again. Now, when you're done with that, whatever your hypothesis is, whatever it is, right? It's either right or wrong. You're going to draw a conclusion. If your hypothesis is supported, test it again. Test it for further experiments or expand on it. Maybe you were close. Maybe you were slightly off. Refine. You can refine it a little bit, but you just keep testing, keep testing, keep testing. What if it's not right? What if you threw that hammer in the air and it just kept going up and up and up? Well, then you'd have to revise your hypothesis, right? Okay. But what happens if you're actually right? Well, at some point in time, after you do research and data, oops, when I did that, it just kind of went towards my belly. When you keep doing it over and over and over again, at some point it becomes a theory, right? At some point it becomes a theory. You've developed a theory. Now, Sir Isaac Newton started off with this process, and all scientists kind of do this naturally. Now, some don't always follow this exactly. Some things are discovered by accident and stuff like that, but for the most part, they kind of stick to the scientific method. Okay. Have any of you guys ever watched Bugs Bunny and the Roadrunner? Yeah. I used to show videos of that when we were talking about gravity. It was always fun. Because there's always a scene where the Roadrunner sets up some sort of trap. Or not trap. The Wile E. Coyote sets up a trap for the Roadrunner where there's like some steel anvil. And then the coyote runs real fast and the anvil doesn't fall. And then the coyote's trying to figure out why the anvil doesn't fall or the cliff doesn't fall, and as soon as he gets under it, falls on him. Anyways, I'm just stalling while you guys write this down, which is fine. Today's physics lesson is brought to you by Awala. I should also point out that if you guys are ever absent, this YouTube video is shared in Canvas. Okay? Can I move on to the next one? No? Okay.
He's actually drawing the pictures.
Well, you don't have to be an artist. Did you draw the little beaker with the chemicals in it and the stir rod?
Yeah.
That's part of the problem. What time do we get out of here?
7 minutes.
Okay. We have plenty of time. We're almost done.
He's done analyzed data and draw completion.
I'm not. I'm almost done.
Right.
Yeah.
I got a question that I want you guys to think about. What happens to a theory and think in terms of Sir Isaac Newton. He has this theory on gravity. What happens if that theory remains constant for a long period of time? Scientists after scientists after scientists have looked at Newton's theory on gravity. What happens to that after time? It becomes something, but if it's not a fact, there's a different term they use. Yes? A law. It becomes a law. So I'm going to move over to the next slide. Can you copy from your neighbor?
Yeah.
Okay. So a law is a statement that summarizes a pattern that's found in nature. All right? I love talking about gravity because it really is the foundation of physics in the sense of how we've come to develop all these ideas. It fascinates me that one man just sat down, something fell, and his natural curiosity made him want to study patterns that he found in nature. And the funny thing is, I can tell you, if you tell me the mass of an object, the planet it's on, and the angle you shoot it at, or how high you drop it from, I can tell you exactly how much time it takes to hit a target and where that target will be, like where it will land. I can do it. And they're algebra based. They're real. Well, if you ignore things like drag and you ignore, I can do it with algebra equations. By the way, you will be able to as well. But that doesn't explain how gravity works. We don't know what causes the attraction. There are some ideas. We know those formulas work. They're the same formulas that NASA uses. We know those formulas work for sure. I'll be honest, NASA uses a little more complicated because they have to think about the air resistance and stuff like that. But it's basically the same, right? You get a pretty good approximation using the algebra ones. And you're kind of right. It does become a scientific fact, right? Fact is one of the, depending on the textbook you get, somebody will say this is a fact, that's a fact. I'm really more concerned with you knowing that it goes from a hypothesis. If the hypothesis is, well, it starts as an observation, then a hypothesis, and then if a hypothesis is proven, then it becomes a theory. If that theory has been proven over and over and over and over again, it becomes a law. So one example of a law is the law of conservation of mass. That has a little bit more to do with chemistry. No, there's one more thing. A model brings things into human scale. It can't be directly observed, or it's a representation of an object or system that is either too large or too small to understand. Has anybody seen the solar system? Has anybody seen a model of the solar system? Yeah, a lot of head nods. So we make models of the solar. Has anybody made a model of the solar system for a middle school science project? There you go, got some hands on that one. Has anybody made the solar system for a middle school project? No, it's too big. You can't really see it with your eyes. Okay? Not the whole thing. And so a model is a representation of an object or system that is either too large or too small for us to understand. Has anybody in here seen an atom or a molecule? Not with your own eyes. Have you seen a model? Has anybody put those things together where they had the ball and the sticks to make them an atom? Or yeah, see some hands? That's a model. I see some people putting some notebooks away. What if I got one more slide?
You told me that you said this is the last one.
I lie, though. I say this is the last one. I don't really remember, to be honest with you. All right, let me see. Drum roll.
Oh,
It is the last one. All right, you guys put your stuff away.